we've mentioned logistic regression as a classifier, and you can use MLE or MAP for that. MAP also gives us this other famous classification algorithm called naive Bayes. And so this is a probabilistic model that assumes that all the features are independent, and that you just use them independently and combine them together to get your class. And so you could be saying and you use thresholds. So essentially you use MAP as we talked about it as logistic regression, but it's kind of its own method that became popular. And it became popular actually for spam email a long time ago, like in the 90s or something. At one point all our email got slightly better because somebody invented this and integrated it into things. It was probably the 2000s, I don't know. So the idea is you've got some label, which is like, is it spam or not, right? This is like true or false. I'll show you some more detailed thing in a second. And then, is it that way or that way? No, it's the other way. And then we could say, well, if this email is a spam, then the probability of certain words would go up, right? So the probability of car would not be affected, but the probability of gold might be higher, or various other words that I won't write here. You know, spam, whatever they're trying to sell you these days, right? There's certain words that would go up, right? And so we talk about, you know, the probability of a particular word. It's just me in very general writing this, given that the email is spam or not, and then the probability of spam in general. We can use that in the way we just did, having these two probabilities to use MAP estimator for logistic regression and build a classifier that says, well, I just look at all the words in your document and count how often they come, and then use this model and try to determine if this email is spam or not. And this is very effective, even though it's a very dumb model, because in language, words are actually related in complex ways. And this model assumes that everything you're using are completely independent. So I'll go into a bit more detail. But I have to switch to web browser for that. Hopefully you can still see that. Oh, it's the infinite window. Yes. I knew that would happen. Okay, so now, okay, you see this thing. So I'm on Scikit-learn, because that's where I'll end up for a lot of these things anyways. They have some very good documentation for stuff. Now this will be interesting. When I switch, oh, because I'm doing the whole window, you can see this. Sorry, testing a new tech. There we go. Good. All right. Just my text window's a bit different. People having good discussion there about neural networks. Jumping ahead to topics. Good. Help each other. So for naive Bayes, like I was saying, I don't know if I have a pen now. Oh, let's stay on highlighter. The reason we use the word naive is because it's got this simplistic assumption that all of the variables are independent, right? So it's not really naive, it's just a simple heuristic that you use, and it works well, right? So if we talk about our usual Bayes rule, here it's expanded out where we've got all the variables, so there's multiple different features that we can have in our data set. And like I said, the stereotypical one for this is to talk about that y is your email spam or not, and x is the counts of various words, right? So you say, how many times does the word the show up? How many times does the word dog show up? How many times does the word gold show up? And emails that have gold in them or money transfer in them more tend to be more spam, right? And so you're just trying to work out any relationship between these features, which are counts of words, and that label. But you could use it for any classification algorithm, right? You could use it for heart data and look at various values of those health features and whether they affect the health of the patient. The reason naive seems like a reasonable thing to say is that it's not reasonable to say that all these words in a document like here, all the words have an order. Now, natural language models, which we'll talk about a bit, at one point in the course, are working really well now because they're looking at how words relate, to other words in the text and all that, right? So like grammar and relationships among them, that's the correct way to do it, right? So a model that basically ignores all that and just says, no, just count them, right? The 15, features 27, value 8. That's what the values are, right? It's dumb, but it's really quite good. I mean, like it works well. So if we break down these probabilities now into somebody's question about the correlation matrix, I'm trying to work it out. I'm not sure. So Xiao Zhou was saying, does the assumption of independent mean the correlation matrix should be 0? The correlation matrix of all of the features with each other, I mean, that counts, I guess, across multiple documents, maybe? So no one enforces this assumption. It's just saying, what you're doing here is you're defining this model and saying, if this were true, if this assumption were true, we could use this model and do the following trick. Because the part that lets us do why we want to do it is that since we are saying that they're independent, if you remember from the probability review class, we can say that a probability of x given y and all the other data, right? So we don't know how they're related. We know that y, all the variables x1, x2, oh, this pen's much better. I like this. If we're writing them as a graphical model, this is what we often do. I like graphical models, so I often write them here. And Kevin Murphy likes them too. So your the textbook that some of you are looking at, he's very big into that. So he probably draws lots of figures like this. This is just one way to say, let's have our random variables and relate them as pictures. And what these arrows mean, right, is that there is a probability in the system that x1 depends on y, right? And x2 depends on y, right? Because that's the true nature of the distribution. But the naive Bayes assumption is that, and maybe I'll change colors. I'm being ambitious. The naive Bayes assumption is that all of these arcs that should exist between the variables don't exist, right? Which is usually false, but it's reasonable and it solves them. It simplifies the math. That's all I'm saying. And since you can do that, you can basically summarize it down to this, right? So you can say that every variable is just dependent on y and nothing else, right? So if you could assume that, then you can simplify the math down, and basically you just get to multiply all of them independently. We have our prior on the label, so say how likely is spam in general? Likely. How likely is the word dog to show up in a spam email? Low, gold, high, money transfer, very high. And we just have these probabilities separately, which we can compute empirically from data, and we multiply them all together, right? And so the true Bayes rule setup of this is this, right? This is still Bayes rule. And then we do the same thing we did with to compute map before, is to say, well, we don't need this, right? Because we only care about maximizing. That's why we're saying here that they're just related. And we come up with a form for essentially map. I guess it said there already. For the problem in the same way, where we've got these independent words and labels, right? And so all we have to do now is estimate these values, and estimating, like I said, the count of a word given spam just requires a data set. Someone gives you, 10,000 emails where somebody has labeled it and said this was spam, this wasn't, and you go through those and you count how many words were in the spam emails, and you can come up with an estimate just numerically as a ratio of these probabilities. And then you could also say, well, how many of them were spam? It's like, okay, 27% of the emails were spam, so I guess that's what that is, right? So it's easy to come up with those numbers. Now, is it easy for me to scroll my browser? That's the real question. I think it is not. So I can do this, I can scroll up. Okay, you can still see it. Does that make sense? We still got our map model, just like before. So once you have that, we can solve it, and then the question really is, are there any other distributions you're going to put on there, right? How do you represent this? What time is it? 4:30. Okay. So in Scikit-learn, they have a bunch of different ones implementing for naive Bayes. They have the model all detailed, so you don't even do anything. But choosing the model has all these implications, right? So you could say, well, we're going to have a Gaussian distribution on what the parameters are, the mean and the variance. The likelihood of a word, basically, you model it with a Gaussian. So you have some count that says, okay, there's a 27% chance that the words money transfer show up in spam, but you have your uncertainty around it as a Gaussian, right? So you'll say 27% as the mean, but there'll be a variance. So when you ask for that probability, you query the Gaussian. Kind of the simplest way to do it is this multinomial approach, which multinomial is just like a histogram, is the probability of each of the values. You literally can specify each one separately. So the parameters for a multinomial are, if you've got 10 labels, it's 10 numbers that add up to 1, and they're literally just separate numbers. So it's kind of the simplest multivariable distribution you can come up with. You don't have to have any fancy formula. And you can update it by having these counts, right? You say, well, how many times have we seen, money transfer in a spam mail? How many times have we just seen a spam mail in general? And you count them. So what alpha and I guess this is different than using a Bernoulli. Oh, right, okay. This alpha is for the problem with zeros, right? So one thing that'll happen here is you've got literally a parameter now for every word that shows up in your document, so there's thousands of them. But some words might not show up at all in your data set, and a 0 is very different than a 0.0001, right? Because 0 means impossible, according to these models. And it could be possible that that word is in a spam email, it's just you've never seen it before. So you don't want zeros in a model like this. You want to have slightly more than zeros, right? And so one way to do that is to basically put counts. So when they put this Laplace smoothing, essentially is all they're saying is that there is no 0, there's only 1. So even if you've never seen an example of that word in a spam email, you always assume that it happened at least once. And since you'll have thousands and thousands, 1 will actually be a very small number. What was I going to look at? I don't know if Bernoulli makes sense. No. So, okay, so that's how naive Bayes works. Let me think if I had another slide that explains something with it. Right, because the last thing we'll talk about is EM. Yeah, we will add this some other time. So this idea, though, of having two different distributions, one as the data distribution and one as the prior distribution, comes up in other kind of areas, and you get essentially this, oh, I have it here already. Oh yeah, this is one somebody just doing text like spam classification on many different methods. And the reason why naive Bayes is always used for this example, because it's good at this, it's not necessarily good at everything, but it's a very simple method to implement, and it can be quite good. And essentially, if you're coming up with a more complicated classification algorithm, you definitely should beat naive Bayes or logistic regression, because why not just use them if you're not good enough, if you're not better than that? So it's a good thing to compare to. So all the ones with NB here are different probability distributions where they're using naive Bayes. This conjugate idea, and I guess I'll try to make sure it comes up somewhere else in the course later, because we're just kind of touching it here. We don't have time to go into that much. But if you think about probability distributions, there's these two things. What we're talking about is like this, right? You've got some distribution of the data, P of x given theta, and you've got your prior distribution, P of theta, right? So in the cases we've looked at, we say, well, we just know what it is, and either we can compute the derivative or we solve it by gradient descent is what we're going to be doing. But if you pick your distribution correctly, then you can solve it analytically. So there's this family of conjugate probability distributions, And like I said, if people are interested or if it fits with something, we can go into it more later, because they're important. They're not the ones that get used essentially for things like deep learning, but for a lot of other methods, they're very important, and they let you simplify the math and the calculations down to the point where you can get exact solutions or one that you understand better. And so they're becoming more important again as people want to have more interpretable models, because you want to be able to say, well, here's the distribution of, my data. It's like binary data because it's just two values, and so I'm looking at like essentially a coin toss, or maybe it's data that that is counts, like this word count thing for spam, and you're trying to figure out, well, what proportion of them, if we just want to count how many there are. Another type is ones where you talk about how frequently do certain numbers come up if they're cyclic, right? And so each of these different types of phenomena, if you know that's the phenomena, then you want to use a distribution that responds to that, right? So Poisson is good for things that events arrive at a certain rate. And if you want to do map or MLE or some probabilistic method where you know the thing is Poisson, then there's a particular other distribution called the conjugate, which fits well as the prior. So it fits well into this map thing. You can do map classification on Poisson distribution and use the prior to be the gamma distribution, which is just another probability distribution, but it fits in place with this one. And so if you use that, then essentially the parameters you pick here match what you're doing, right? So when we talked about counting, where is counting? Multinomial. Multivariate? No. I had it before. Sorry, this thing's sitting in front of my keyboard. That's not good. Dirichlet, categorical. Okay, well, here we go. So in the case where multinomial, you're saying like we're just counting how many times each of the labels occurs, you can just put the counts on top like we did, or you can use Dirichlet distribution instead of the count itself. And that's kind of does this next level. And on top of that, you can basically say, well, how big, how many, the parameter used there is how many occurrences are there in the category. So how many instances of this label are there? And that helps you set things up in the right way so that the math works out and you can solve it exactly. So it's just a thing to look into if you're getting into using these methods for comparisons and analysis. These conjugate distributions are important to be able to look up and use. But I won't, this is too vague for me to say I'm going to test you on what they are. If we're going to have questions on this on our thing, we'll go into more detail. Or we'll give you an assignment question where we use it in a very particular way, and I'll say use this one or pick the right one. So we'll figure out the right way to do that. And I hid my screen, so I haven't seen if there's any questions. There aren't. So we're coming up close to time. Well, I guess we don't have to. Usually in classes we end 10 minutes early, so people have time to get to their next class. I mean, that's not true here. What else did we have? Oh, I had a little bit more slide. If I can remember where my screen is. Okay. So the last kind of thing along these lines is this idea of missing data. And you guys are doing some data cleaning on the assignment. And so one thing you can do is often say is like, well, there's some data missing, so I can try to fill it in or remove those rows or data. But you'd like to have some methods that basically are a little robust to incomplete data, right? How can you still use the data you have, but not necessarily have to have all of it available? So anything that works like that is going to probably have to be a bit more iterative, something that basically tries out a certain value and then moves around. So expectation maximization is kind of one way to do that in this parameter estimation approach. EM in general is a much more general method, so it can come up in many ways, and you'll see in a minute because the algorithm is very simple. It's more of a meta algorithm because it's like it can be anything as long as you follow these two steps, right? So what it does is that you find initial estimates for the parameters or whatever it is you're trying to fit. You guess, right? That's what it comes down to. You come up with a guess. and you take a guess, and then you update your guess based on the data you see and move slowly towards a better guess, right? Now, this isn't usually following something where necessarily following a gradient, but a gradient approach could be kind of one way to think about this. But here we are really like trying out each value. So for our kind of approach for MLE or MAP, you could basically propose, the values for the mean and the variance of your Gaussian, try it out and see how well the probability comes out for your data, right? And then you try to update the values so that you kind of move closer to something. But you don't really need the actual gradient itself because you're just basically using averages. So the two steps are to estimate and maximize, right? So you give your initial estimates for your parameters. You calculate that value, you carry out the formulas, and then see how well it works. And then you do something to update it, improve your values. So this is really the entire of the EM algorithm. So that's why we call it a meta algorithm, because the way you do your estimation and the way you do maximization could be anything, and it would still be EM. But this general idea is useful in many different places. And we have another threshold, though, so we have another parameter now, which says you should stop at some point and not just go on forever, because you could just keep improving. But you assume that basically once the change goes below a certain value, you stop. So you wait for it to converge, or at least stop changing so quickly, and then you stop. Now, it doesn't mean you're at the optimal value. It doesn't guarantee anything, but it does something. It moves you, and it usually actually works fairly well. So we have some very simple partial data set with missing data. So we have these values, and we know there's a couple data items missing. We don't know their values, so we're trying to basically estimate what the missing values are that should be fitting inside somewhere here. And so if we assume that the data has some normal distribution, we could do MLE at each, come up with that formula and say, well, we're going to build our estimator for mu in this case as just the empirical mean of the values that we've seen. We take the values we've seen, we say the average, say, well, I assume that the mean is the average of these values, right? But I'm going to guess what the other data points are first, right? Yeah, so we're going to guess that the initial mean is something in between. We just come up with some number, 3, and then we say, okay, so it's 3. That means then the value of those missing data should be 3, because if they're at the mean, and then we compute the new average, like the new mean is actually all the data points, right? So we take the ones we have plus the new ones that we kind of our guess, right? The actual data and our guess data, and we come up with a new mean, right? And so now this one is also wrong, but it's taken this guess into account. And then we start over here and basically recompute it again. But now we use that updated mean as our value to fill in for those numbers, and keep doing so. And so then basically without having these missing values, we're trying to build an estimator for the mean of the data without ever having to see them, right? And what we're going to do is keep trying out different values of the mean and then saying, well, if it were, we'd now basically put those in as data, compute a new mean, and so on. And if you keep doing this, at some point you're going to converge down to a value that doesn't change very much and gives you a new estimator of the data. So you're really, it's extrapolating. It's like coming up with new data points, but if no one told you that the missing data was between these two data points or between these two, they just said there's 2 data points missing and we don't know what they are, what would you do, right? So this way you basically keep coming up with new mean estimators, guesses, and you're not doing anything magic because you're still kind of extracting what the most reasonable mean is from these data points, but you're in a sense instantiating that guess and seeing what would happen and then trying it out, right? And so that's why you can kind of use MLE, because you have the whole data set that you've been given for that. Hopefully that makes sense. All right. Yeah, and so I should have a slide where all of them are not faded out, so you can't see them all as well here. But so that's the end of that topic. So we've got been talking about data and kind of probabilistic ways of representing the relationship of the data, trying to build a model of it. It's kind of the simplest machine learning we could do, where we say that we know there's a model, we're going to have all these assumptions, and we're trying to fit some parameters to it. So the other methods we're going to be going on from here will have the same feel, right? There's still going to be kind of a function over some data, given some parameters, and it's going to give us the output which we want to use as labels for classification, or values for prediction, or something else. And how do we get these parameters? In this way, we kind of used mathematical probabilistic ways of doing it. Next week, we're going to talk about decision trees, where we say, let's divide up the data in very particular rectangular blocks and keep subdividing. And every one of those divisions is defined by various splits and relationships. And that's essentially what theta is in that sense. And then we'll talk about other methods, but the same approach applies. And like something we said on one of the slides, you can mix and match, right? So there's no reason you can't use, a decision tree where, at one of the leaves, it's actually doing map estimation on the data, or another leaf, it's using a neural network, right? So data is data, and labels are labels. So we're learning basically different tools we can use for this, and we can mix and match them together for solving our problems. But each one we're using is kind of its own category. So this is the category of these probabilistic methods for parameter estimation, and hopefully people found it useful. So I'll post these ones up tonight once I've processed it, and we'll move on from there. Hopefully everyone else is doing well wherever you are. We had snow here in Waterloo. I know not snow for everybody in different countries, but hope things are going well. And the assignment, you're halfway through it now, of course. If you haven't, you should download it and take a look. You've got till next Wednesday for that first assignment. And we'll release the second assignment the same day, and it'll be using some of the methods we're talking about here, as well as some of the things we'll talk about next week. So hopefully everybody's good. If there's any other questions, we'll talk on Piazza. Thanks for coming.